In this workshop, we've looked in quite a lot of detail at the technical approaches that we can use to fit, select, and validate hydroecological models. But we shouldn't forget that the end goal of modelling is to develop something that we can use for practical purposes. And whilst hydroecological modelling can be useful in an academic sense to provide new understanding about how ecological systems respond to changes in flow, from a practical water resources management point of view, we want models that are capable of making reliable predictions of ecological responses under different abstraction or flow scenarios. But before I explain how we can do that using the HE Toolkit, I'm going to hand you over to Mike Dunbar, who's the former team leader of the Environment Agency's Hydro-Ecology team. And Mike's going to tell us a little bit about some of the Environment Agency guidance that's available to you to help guide you through the development and application of hydroecological models. So over to you, Mike.
Hydroecological modelling has matured in recent years, from applied research on regional and national datasets in the mid-2000s to the application of the tools in specific local areas more recently. As a result, hydroecological modelling is now a suggested approach to get the most from available data for defining local environmental flow constraints for flow recovery, for low deterioration investigations, and for new licence applications. It could also be applied to drought permit environmental assessments. Where your interest is a limited geographical area, modelling can be undertaken focusing only on data from an individual site, providing there's sufficient data available. Sometimes that's the only option, particularly in the lower reaches of larger river systems. But in many cases, that site data can be boosted by data from a range of similar sites. This is especially the case if you want to use your model to make predictions. That's where the approach outlined here is most beneficial. Finally, if you're interested in a wider geographical area, then the same thing applies. The modelling approach provides a framework for looking at which watercourses are most sensitive to water abstraction, understanding the relative importance of abstraction versus other anthropogenic pressures, particularly when the focus is regional planning. The toolkit facilitates this process, but as you've gathered, it's not a cookbook for determining the flow. It's about getting the most from existing monitoring data, automating the tedious steps, thus allowing you to focus on the most important parts of a study. It's also useful to highlight where to focus efforts on additional data collection. If we could produce further firm guidance at this point, then we would. In practice, guidance will need to be updated incrementally as the number of multi-site studies increases.
Thanks, Mike. So once we've got a model that we're happy with, that provides a reasonable representation of our data and meets the assumptions of our modelling approach, we're then in a position to use that model to make predictions. A useful starting point is to use the model to make predictions under the historical flow conditions. Plotting up the measured biological metrics and the fitted values from the model as a time series provides a really nice visual way of summarising the strength of the model flow effects and also the overall performance of the model. We've got a simple example on the slide here, which is based upon the same 4 data sets that we looked at the beginning of the workshop when we were introducing the concept of linear mixed effects modelling. We've got a model that we fitted to the data, which has 2 flow variables representing Q95 and Q10 effects. And both those variables are included in the random part of the model. So the strength of those hydroecological relationships can vary from site to site. A simple way of extracting predictions from the model, including a prediction interval, is to use the predict interval function from the MERTools package. This provides us, as I say, with a central estimate, a central prediction of the, in this case, the life OE ratio for each sample in our dataset. And the prediction interval, which we can tune, describes the range of values within which we are confident a certain percentage of our data will fall. Here we've chosen to configure that prediction interval to a 95% interval, And you can see that that means only about 5% or 1 in 20 of the individual observations, represented by the black points, fall outside of that prediction range. What's particularly interesting to note is to look at the responses across the 4 sites. The sites in the top left and bottom right corners are relatively insensitive to flow. They have very weak hydro-ecological relationships. And there you can see that the predictions, as shown by the red line, are fairly flat. By contrast, the sites in the top right and the bottom left-hand corners are more sensitive to flow. And you can see the predictions, the red line, fluctuate over time in response to changing hydrological conditions. The predictions pick out quite nicely how the invertebrate community at these sites has responded to high and low flow events. And particularly, it's possible to pick out the effects of the 1995-96 drought, the 2004 drought, and the 2011-12 droughts. The degree to which the red line fluctuates shows the overall effect that flow has on the invertebrate community. And seeing how close the individual black points, the actual observed data, are to the model predictions also provides a visual way of telling us how well the model is able to represent the temporal variation that we see in the data at each site. Not only can we use our calibrated model to predict ecological responses under our historical flow conditions, we can also use it to predict the response under alternative past flow regimes, i.e. a sort of what-if analysis. Or we can simulate a future flow regime and predict how our ecological community, our biological metric, will respond under those new conditions. As a very simple example here, we've simulated the effect of maintaining a compensation flow in the river to deliver a certain minimum flow. To do that, we've constrained the Q95 flow statistics in our model so that they can't drop below a certain value, and then plotted up the predictions under this new flow scenario. These are shown by the blue line on the plot and can be compared with the red line representing what's happened historically. We can see that 3 of the 4 sites, the blue and red lines, are virtually identical. This indicates that imposing a minimum flow in the river would have little or no benefit for the invertebrate community. But for the 4th site, in the bottom left-hand corner, we can see that there is a marked difference between the red and the blue line, particularly during periods of drought. By comparing these 2 lines, it provides a quantitative indication of how much improvement or change we might see in the life-OE ratios if we were to impose a different flow regime at this location. We can also use models to make predictions for new sites. Typically, we calibrate our model to sites where we have monitoring data, but we may wish to make inferences about the state of the invertebrate or biological community at other unmonitored locations. To do this, we can make predictions using only the global, the fixed effects part of the model. The random effects relate only to the specific sites in the calibration dataset, but the fixed effects are common, they're generalizable, and they provide a basis for making an extrapolation or prediction for new unmonitored locations. When using hydroecological models to make predictions in this way, we do strongly recommend using the models to make relative comparisons under different scenarios, just as you can see on screen here where we're exploring the effect of altering a compensation flow. By doing this, we're able to assess the degree of change between 2 different scenarios rather than try to make predictions of absolute status. Working in this way means that we are able to essentially isolate the effects of flow, and we're simply making comparisons between 2 different flow scenarios. Whereas if we want to make accurate predictions of absolute status, that relies on the model not only being able to describe the effects of flow, but also being able to describe the effects of other pressures acting on the system, such as water quality or habitat degradation. And whilst that might be possible, that's a more ambitious goal of this kind of modelling exercise. And a safer course of action is to try and focus purely on isolating the effects of flow. Hopefully that's just whetted your appetite for what is possible with hydroecological modelling. There's no limit really to the range of scenarios that you might wish to explore. For example, you could explore the effect of a change in compensation flow, a hands-off flow, a change in abstraction rate. All of those different influences can be modelled, and the predictions allow us to quantify how much we expect our ecological system to change in response. So to conclude this second workshop, I'd like to just summarise really a few take-home messages. These are simple tips that we found from practical experience make the whole process of developing and applying hydroecological models that little bit easier. The first thing we would always recommend is making sure that when working in R, that all your packages are up to date. This ensures you're using the most up-to-date and bug-free versions of these packages. When you're installing the HE Toolkit itself, we would recommend installing it into an empty RStudio project. This gives you a blank canvas and a space within which you can build your project and provides a place for storing your data, your analysis scripts and your outputs. Packages do update over time, and to ensure that your workflow is reproducible, you can use the renv package. This is a package dependency manager which, once installed and activated, maintains a snapshot record of the different versions of packages that you've used in your analysis. This means that if you hand your analysis over to a colleague or a client to run themselves, and they're using a slightly different system with different packages, or if you yourself want to revisit the analysis in the future, you can be assured that your analysis will be entirely reproducible using exactly the same versions of the packages that you used to first develop your model. You will have noted, perhaps as we're going through the slides, that the HE Toolkit does use some standardized column names. For example, flow site ID to represent different gauging stations, or biology site ID to represent different macroinvertebrate sites. This is deliberate, and it means that the outputs from one function can then go seamlessly into the next function in the workflow. You don't have to use these standardized names, but they're designed to speed up and make the whole process of importing, processing, visualizing and analyzing data that much more streamlined. When you're assembling the data, you will often find that when you're importing data from different sources and joining it together, you will end up with a very wide data set with a very large number of columns of data. Dropping redundant columns from those imported and joined data sets makes the whole process a bit more manageable. It means that when you're looking at your data, you can focus in on those columns which are really relevant to what you're doing without getting distracted with a lot of redundant and unuseful information. Whilst it can be quite tempting once you've assembled all your data to jump straight into building some models, I would also always caution about doing that. And in my experience, it's always worth spending a little bit of time really getting to know your data. So when you build the model, you've got a really good understanding about, for example, which predictor variables are correlated with each other, what distributions your data follow, and whether any transformations might be necessary. Are there any missing data or outliers? And how much data do you have? How many sites do you have? And is the number of samples relatively well balanced across sites, or do you have some sites which have got a lot more data than others? Armed with that knowledge, you're in a much stronger position to determine what sort of modelling approach you need, what sort of error distribution you need, what transformations you need, and also to take decisions about which flow predictor variables are likely to be most useful. Finally, I would just like to emphasise that this training course is very much a crash course. We've skimmed the surface of some very extensive and complex topics. And if you're embarking on hydroecological modelling using mixed effects models, you should do so with a good foundation knowledge of multiple linear regression first. Don't skimp around on reading around the subject. There's a lot to learn and some very useful resources out there. And armed with that knowledge, you'll be in a much better position to be able to judge how to configure your model to get the best out of your data. There's plenty of pitfalls, and if you're uncertain about how to proceed, then it's always wise to consult with a statistician who can guide you through some of these decisions. With that in mind, we wanted to signpost you to some further sources of information which can allow you to dig down and get a deeper understanding of some of the topics that we've covered in this workshop. Listed on the slide here is, first of all, a paper which provides a really nice, accessible introduction to mixed effects modelling, and also the use of multi-model inference for model selection. The book by Alan Zur is a bit of a Bible for mixed effects modelling and how that can be applied within the R environment, and provides lots of very useful practical guidance for applying this kind of technique. If you get to a point of using mixed effects models in R and you can't find enough detail or enough guidance about the technicalities of fitting and validating models, then there is a lot of information online. A good starting point is the FAQ website maintained by Ben Bolker, which provides lots of very detailed information about fitting linear and generalized linear mixed effects models. If you've got a question about exactly how to configure a model or how to deal with some of the warning or error messages that come from R, then you can be assured that someone else has probably asked that question already, and there's a good chance you'll be able to find an answer on that website. I've also linked on the slide here references to a few papers which provide a nice illustration of how hydroecological modelling can be fitted to some real-world data sets. The first two are papers led by Mike Dunbar, which provided the impetus for a lot of the hydroecological modelling that's been undertaken over the last 10 plus years, and also provided the inspiration for developing the HE Toolkit. Those papers focus on being able to model invertebrate communities using the life metric as an indicator of invertebrate community composition. And they focus on how river discharge interacts with local scale habitat features to drive patterns in the data. The third paper is by Judy England and her co-authors, and is slightly more recent and focuses on the use of the MIS index. It's a particularly interesting paper because it focuses on ecological responses to flow intermittence. So it's dealing with intermittent river systems and suggests some useful techniques for modelling the effects of drying events on invertebrate communities. Finally, to wrap up, I hope this workshop has inspired you and given you some useful knowledge to get you started using the HE Toolkit to apply hydroecological models. If you need help on any of the functions that we've covered in these workshops, then a good starting point is to bring up the package documentation. Each of the functions has a help page, which you can access in the R console by typing question mark and then the name of the function. This will give you a lot more detailed information about the different arguments, the inputs to the function, the calculations performed by the function, and also what it outputs, as well as some example code that you can run yourself to explore different ways of configuring the function. We've also developed a vignette, which is a detailed case study which illustrates the application of the HE Toolkit all the way from data import through to fitting a final calibrated model. On our GitHub page, we will also soon be posting some shorter case studies which just illustrate how the approach that we've covered in these workshops can be applied to different ecological data sets to answer slightly different questions. If you find that these resources are not sufficient and you have more bespoke requirements for training or support, then please feel free to reach out either to ourselves here at APEM or to the Environment Agency, and we'll be able to direct you to additional sources of help and support. The HE Toolkit is still a relatively new product, and these training courses and videos are part of an effort to disseminate the tool and help practitioners get to grips and apply it in a real-world setting. However, we would really much appreciate the feedback from you, the users, to let us know how you're getting on with the HE Toolkit. Does it give you what you need, or have you got any suggestions for improvements or refinements? If you encounter any issues or any bugs or have any suggestions for feature requests or improvements, then you can get in touch with us, the development team at APEM, either via our GitHub page. So if you have a GitHub account yourself, you can log issues and suggestions via the Issues tab. Or alternatively, if you prefer, you can contact us directly via email. And we've set up a dedicated email address, hetoolkit@apemlimited.co.uk. That will ping a message to myself and the rest of the development team here, and we'll respond to you as soon as we can. I hope you found these workshops useful and inspiring, and thank you very much for watching.